In Chapter 5, we're going to be talking about continuous distributions. And the important and most important continuous distribution that we will talk about is what we call the normal distribution. We will use this distribution very frequently throughout all of the remaining sections and chapters that we cover in this class. Now, a normal distribution, as I state here in the box, is a continuous probability distribution for a random variable of x. The graph of a normal distribution is what we call a normal curve. So remember that continuous distributions will be represented by curves, whereas discrete distributions we thought about as being organized in a table, like we did with the binomial distribution. So here are just a couple quick properties of what a normal distribution, or properties of a normal distribution, and what it has. The mean, the median, and the mode are all equal. As seen here below, it has a bell-shaped or symmetrical distribution. So you can see that this might relate back to ideas of the empirical rule that we talked about much earlier in the semester. The total area underneath this curve is equal to 1. So if you were to shade all of the area under it, you would get a grand total of 1, and that represents a max total 100% in terms of probabilities. So probabilities that we're going to be measuring are going to be represented by areas under a curve. Okay, the normal curve also approaches, but it never touches this horizontal x-axis that I have over here, which is kind of weird because even though then I can shade underneath it forever off to the right side and forever off to the left side, I still only have total area under it of 1. And for any of you who have possibly taken a calculus class before, you may be interested to see in this idea of inflection points still arise. If you've never taken calculus before, don't worry too much about it. An inflection point is actually just going to be a spot on the curve where kind of the bendiness of the curve changes. You can see between these two dots, this curve is kind of bending downward. And after this dot, you can kind of imagine the curve beginning to start to turn, so it's going to like bend back upward. At least that's what it looks like is happening, and those are the spots in the graph where that kind of change happens. Now, down here I have a big scary function for how you would actually graph a normal distribution. We'll never use this function, it's just here so that you can appreciate just how simple what we're going to do in this section actually is, because we're going to actually hand off all of this information to calculator programs and let the calculator do all of the heavy lifting with the big scary formulas. Okay. So let's take a look at what every single normal distribution has. That is, we want to take a look at its parameters. Every normal distribution with one of these nice bell-shaped curves is always going to have a mean and a standard deviation. So these are the two important parameters that we're going to be working with. Now, when we talk about this mean and the standard deviation, they affect the way that this picture looks when we go ahead and sketch it out. So if you were to take a look over here at this little applet, you can see that I have a normal distribution kind of sketched out over here. And you can see that my average right now is set at the value of 0, and up here you can see my standard deviation is 1. Notice over here I can slide around what the value of the average is. And notice that as I slide it, the entire picture, not the number line, but the picture itself, will kind of slide, so it'll be centered above the appropriate value. So notice I could slide the average down to 2, so now it's directly above the value of 2. I could slide it all the way up to 1.6, and now that's where it rests. Or of course I could go ahead and reset it back to 0. The standard deviation is just going to affect kind of how stretched out left to right or scrunched up left to right our curve is. So right now you can kind of see that my curve here has these markers that every time I go out kind of like a jump, that's a unit of 1. But notice that I could increase this maybe to say 1.5. Now if I do this, it's going to make the curve a lot wider and a lot flatter, whereas if I was to go in the opposite direction, maybe down to something like 0.5, my curve is going to get a lot taller and a lot faster, be a lot skinnier overall. So standard deviation is going to have this particular effect on a normal curve. So take a look down here at example number 1. Consider the following normal curves here in this picture. I might be interested in which curve actually has the smallest mean. Now, of course, if I want to answer this, I would have to go look at the number line that's presented down here near the bottom. I can see that I have values of 0, 1, 2, up to 5, and all the way down to negative 5. So which of the curves, either by color or by their actual name, are actually going to have the smallest average? Well, if you said y2, which is the green one, then yeah, you would be right. Y2 has the smallest average, and its average is -2. I can see that that's exactly where it lands on the number line, right above -2. It looks like the average on all the other ones are actually identical. They're all at 0. Now, which of these normal curves has the greatest standard deviation? Well, that would actually be Y4. That's our yellow-ish kind of one, maybe yellow, yellow-orange. But this big, wide one, remember, the wider the picture is left to right, the larger the standard deviation is. Of course, I can't really tell exactly what the standard deviation is by looking at the picture. That's not easy to do, but I can definitely confirm it has the largest. Could you tell which one has the smallest? Well, if you answered Y1, you'd be correct, because Y1 is the skinniest and tallest distribution that I have out there. So again, all of these are normal distributions. They're just normal distributions with different averages and standard deviations. In the next video, we'll take a look at how we can actually compute some probabilities using normal distributions.